Okay, so we saw how light behaves as a wave. Okay, it has a wavelength. The distance between successive troughs or successive crests is called the wavelength. Visible light has a very short wavelength. It's 400 to 700 nanometers, basically half a millionth of a meter, or half a thousandth of a millimeter. The frequency is the number of waves passing in a certain amount of time. That's measured in hertz. And of course, if you multiply these two things together, you're going to get the speed of the wave. And in the case of electromagnetic waves, you're talking about the speed of light, which is the fastest speed that anything can travel, about 300,000 kilometers per second. Now, the speed of light is frequency times the wavelength. So that means that if you change the wavelength, you will also change the frequency because the speed of light has to stay the same. And this makes a lot of sense because think about it. If you stretch out the wavelength, if the wavelength gets longer, that's like being out on the ocean in a fishing boat or in a little rowboat, and the waves are all stretched out. You will be going up and down very slowly as the waves pass you by, right? The waves pass by, you'll be going up and down with very low frequency. On the other hand, if the waves are very short, if this gets smaller, then you'll be bouncing up and down with high frequency. Okay, when the waves are choppy, this is called when the waves are choppy. Choppy waves are short wavelength waves, and you'll be bouncing up and down with high frequency because they come by very, very quickly and very rapidly. Okay, so this means that the wavelength and frequency of light are inversely related. Right. Now, in addition to the wave property of light, light also behaves like a particle. Now, this is kind of weird because waves are a spread out kind of thing, and particles are a very localized kind of thing. Okay, so a beam of light consists of these tiny little energy packets or particles. Now, we're used to thinking of matter is made up of indivisible bits, which we call atoms. Well, light is similar. If you have a beam of light, there's a tiniest little bit of light that you can call a particle of light. And in fact, we call these little massless particles photons. They are not solid particles. They are not massive particles like an electron or an atom would be. They are just little, you can think of them as little energy raindrops, if you will. Little blobs of light. But unlike a raindrop, you can't cut one in half. There's a certain amount of energy it has, and that's what it's got. Now, it turns out that the energy carried by a photon depends on the wave property, depends on the frequency of the photon, but also on the wavelength. And since those two things are inversely related, then the energy depends either directly on the frequency, meaning high frequency is high energy, but it also means that it's inversely proportional to wavelength. So if you have a big wavelength, you have small energy. If you have a small wavelength, you have high energy. Okay? So the energy of a photon is directly proportional to frequency. Okay? High frequency light carries a lot of energy, and the energy of the photon is inversely related to wavelength. Okay? So light with a high frequency and a short wavelength carries great energy. Okay? The example of this would be like ultraviolet, X-rays, and gamma rays. All of these types of light have very, very high frequency and very, very short wavelength. This is why these guys are dangerous, by the way, because every single photon packs a punch. And if those photons interact with the cells of your body, they can screw up the DNA, they can screw up the molecular structure of your cells and cause cancer. And that's why these are to be avoided if possible. Okay. On the other hand, light with low frequency and long wavelength carries very little energy. Okay. For example, this would be like infrared, microwave, and radio waves. Okay. These guys won't hurt you unless they're very, very high intensity. And they can't do things like screw up the molecular structure of your cells because each individual photon doesn't pack enough of a punch. Okay, so what this is telling you is how much of a punch does this photon carry. If the frequency is low or the wavelength is long, then you're going to get low energy. Okay, and the reason I'm doing this in red, by the way, is red is a low energy color in the visible part of the spectrum. Okay, on the other hand, if the frequency is high or the wavelength is short, then you get high energy. Okay, and so that's a thing to keep in mind. To keep in mind that in the visible part of the spectrum, the blue and violet colors are the high energy colors, the reds and oranges are the low energy colors. Similarly, with the other types of light that we can't see with our eyes, it's the X-rays and gamma rays and ultraviolet, the short wavelength, high frequency types of light that carry great energy, and the stretched out waves of radio and microwaves and infrared that carry less energy per photon. Okay. Now, they say a picture is worth 1,000 words, so a chart is probably worth maybe 100. Here's a nice little chart. Okay, this chart shows the different types of radiation, and this is not to scale. And by the way, this stuff on the top, the wavelength, you do not have to memorize that. I'm just putting that down to give you a rough idea of where these various forms of light fall in the spectrum. But you should know the order. Definitely make sure you know the order. And this is listed from redder to bluer. Now, even though radio waves don't have a color, we say that they're on the red end of the spectrum because they're beyond the red end of the visible spectrum. Same thing with gamma rays and X-rays. They don't have a color per se, but because they're beyond the blue and violet end of the spectrum, we say that they are bluer. Everything on this chart to the left has a longer wavelength. Everything on this chart to the right has a shorter wavelength. Therefore, everything to the left also has a lower frequency, and everything to the right has a higher frequency. And the most important thing is that the things to the right have high energy and the things to the left have low energy. So make sure you know that infrared has less energy, for example, than visible light, and visible light has less energy than ultraviolet, and gamma rays have the most energy of all, and that sort of thing. Also, when you talk about the visible spectrum, the right-hand side, the blue and indigo and violet, have high energy, and the red, orange, and yellow tend to have lower energy per photon. Okay? So these are the kind of dependencies you have to remember when we're talking about the analysis of astronomical objects using light.